he has sent you an email that he will be available on Wednesdays and Fridays in room 2.280 in the engineering building from 11 a.m. to 1 p.m. Right? His email said 11 a.m. to 1 a.m. So please ignore that 1 a.m. He's not going to stay all day for you guys. It will be 11 a.m. to 1 p.m. Right, Mansoor? Your email said 11 a.m. to 1 a.m. And today is lab 2.
Yeah, my email might have a typing mistake in there. I meant to say 11 a.m. to 1 p.m.
Yeah.
Just 3 hours.
We will not be, we don't expect you to stay there all day. Don't worry. All right. So today let's get started on lab 2. Yeah, there was somebody asked me when is lab 2? Of course, we didn't have class last Monday, so today is the second class. But anyway, things have been streamlined to a whole bit. So let's get started. You guys can see my PDF with lab 2 on it. All right. So today we'll talk about what is a series circuit and what is a parallel circuit, and how do we make series circuit and how do we make parallel circuit, and what is the voltage and current behavior in a series circuit or a parallel circuit. So now series name tells us a lot. Series circuit is when we put components next to each other in series. So we'll talk about resistors. We'll get started with the resistors. If you put two resistors with one side of one resistor is connected to the other side of the other resistor, and then the voltage is going across, we call that a series circuit. And if two resistors are connected to each other and they're connected to voltage source, we'll call it parallel resistor. We'll look at the example. And it's important for you to be able to translate the circuit which is drawn on the paper on the breadboard, because you'll have to follow the cables and you have to see the connection to understand if it is a series connection or if it is a parallel connection, because in both cases, the voltage and current behavior will be different. In both cases, our goal will be always to simplify the circuit. So if we have a bunch of resistors in series, instead of dealing with each resistor, we want to sum them up on our paper mathematically and treat them all to be as an equivalent resistor. It makes our life much easier to deal with an equivalent resistance than dealing with each individual resistance. So in the same way, if there are a bunch of resistors which are operating in parallel, we want to find out the equivalent resistance for them also, so we can apply our Ohm's law easily. Ohm's law. We all know Ohm's law, right? V equals IR. Together on this, so voltage is equal to current times resistance value. And now when you have bunch of resistances, let me just show you first picture. If you have bunch of resistances, here we are just showing two, but of course, when we go ahead in this, we'll see in this lab, there'll be a bunch of resistances that will be there together. So some of them will be in series, some of them will be in parallel, but our end goal is to put them all together mathematically to find a total resistance that a circuit will provide to a voltage source, because that total resistance will help us then know that what kind of voltage source we need and what kind of current do we expect. So of course, these are simple circuits that we are dealing with, right? So material for this, all right, so that's the objective. So we want to be able to use our knowledge to compare theory with real numbers. So theory is Ohm's law, and real number is what you will measure with your multimeter. And we want to become skilled at identifying if it is a series circuit or a parallel circuit. And then if you identify, then we want to calculate and measure voltages and currents and probably see how much off is our circuit from what we expect. And we'll apply Kirchhoff's voltage and current laws, KVL and KCL. That's what we call them affectionately, right? So have you guys studied KVL and KCL in the lecture? All right. All right. So when I will say KVL, I expect you to know from theory what am I talking about. And when I say KCL, all right. So Kirchhoff, there are many different ways how it is pronounced. Right? We'll stick to KCL and KVL. All right. So we need 9-volt batteries. We need a handheld multimeter, which you already have, breadboard, and leads. Resistors. All right. So my suggestion is once you've got a bunch of resistors from the TA, maybe 10% up or down. We may not get exact resistor that that the handout says. But if it is close enough, that's okay. Then in your report, you identify, okay, instead of getting 335 ohms, I got 320 ohms and I'm using that one. That's perfectly fine. But what's important is once you get a bunch of resistors, you need to save them. Easiest way for me is what I do instead of looking at each one of those and trying to read up, I take a bunch of those Ziploc baggies and I write them with Sharpie and I just put them in Ziploc baggies. I don't want to read up again and again. I just put them in Ziplocs. Small baggies, I don't know, smaller than sandwich kind of things. So you got a bunch already, you can get more. Of course, Wednesdays and Fridays, TA will be there from 11 to 1. Now you have to create those circuits. So before the lab, you have the understanding from your lecture, the how we how does a series circuit behave, how does a parallel circuit behave for current and for voltage. Right? So once we have that, then we can start cranking up these circuits and start doing the measurements. I see one student in her car. This is the lab time. This is where we actually do things. That's where TA and I stay here. Last time also we stayed till 4 o'clock online available. At least there was one student who was doing the lab. So our expectation is for you to do this while we are here. All right, so this is recapping the theory, a series circuit in which resistance are arranged in a chain, and the current is the same through each resistor in series. So I say, in simple example, if you have two watering hose for your lawn, if you two put hoses in series, you open your tap, the same water flows through the whole network of hoses, maybe n number of hoses you put together, right? But at the end, the pressure if you put too many of them together, the same water will flow, but the pressure at the last one will be probably less than what you would have at the start of the tap. Let's just stick to the current concept here is that, so if you open the tap, the same water will flow through all the hoses. But if you use this 1 to 4 kind of thing, like they sell at Walmart or Home Depot, and you have 1 in, 4 out, what's going to happen to the amount of water flowing through the, so if you have say 5 gallon per minute coming, 4 gallon per minute coming, and you have 1 to 4, what kind of flow do you expect from each 4 hoses that are connected? So let me give my example again. So if you have a tap of water in your garden and you have one pipe coming, one hose coming, and then you use this 1 to 4 kind of fixture they sell at Home Depot, and you apply 4 hoses in the front. You are getting 4 gallons per minute coming, and now you have 4 divided into 4. Will you get 4 gallons in all 4 of those? What do you expect? Probably if they are same size, you will get 1 gallon per minute each, right? Approximation. But the idea is that the current if you think of the same thing like a current, the current will get divided. But if you put them in same length, one after the other, then you get the same 4 gallon per minute possible. So that's a simple analogy for a series uh, connection. And for parallel is that is the what I was talking about, that you divide one uh, pipe flow into four, which is the resistors are arranged with one of their terminals connected to that together and the remaining terminal connected together. So so now you have one wire coming and you have bunch of wires that you distribute and you put resistance on each wire. And at the bottom, you may clamp them together or you ground them all together. So that's the case what we call as. So in this case, the current gets divided, but the voltage stays the same across all of those branches, across all of those resistors. So if you hammer this concept down, then it becomes easy for us to do the calculations that go with that, right? So, all right. So first equation, this is nothing but Ohm's law. So V Ohm's law, V equals IR. So here we have just split it and we have written uh, the other way around. We said, okay, what is the current? We say, okay, then take R on the other side. It becomes I equals V over R. Now, many times we will be using these subscripts, which are nothing but helps us to see, okay, where is this current coming from? So here we said power supply current. So supply, we put subscript S, power supply current. And he said voltage, again, power supply voltage. And then we put EQ for R. What would be the EQ here? What would EQ mean here? Can somebody, all right, Manuel, I can't see you. Juan, your video is off. Francisco, Fernando, your video is off. Let's turn your video on and tell me, why would I put EQ here? EQ with resistance.
Uh,
Equivalent.
Equivalent, right? So there can be bunch of resistance, but from the point of view of power supply, I want to see, you may have bunch to maybe 20,000 resistances, but for the power source, we want to see what is the equivalent resistance of all of your resistances that you may be using. So we use EQ there. So, so this is from the power source point of view, but now when we'll get into circuit, then we'll start more of divide and rule. We'll take smaller parts, get the resistance, then bigger, 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 bigger. Ultimately, we'll get the whole equivalent resistance. So we use the combinations for equivalent resistance. If we put them in series, we just add them. R equivalent is equal to R1, R2, R2, 3, as many as you want. So for this, the condition is that when you have one resistance connected with another resistance, we should not have any connection in between. So it should be just these two, one connected to the other without anything connected in between, right? So they have to go through straight. No more sub connections there. So in that case, you can just simply add them up. Now, this is a very simple thing to do when you have a bunch of resistance in series and directly connected with the power supply. But alas, it's not simple in the real network. There are always more connections here. So we have to then divide and rule. Now, when you have them in series, the current is the same through all the resistances, right? But I haven't said anything about voltage yet. I have just said current is the same, right? Now, if I would have to look at the voltage, then there will be, suppose there is a voltage applied across these two resistances. The voltage will be consumed by each resistor. differently. If the resistance are of different value, then the voltage consumed, or what we call as voltage drop, would be different across each resistor, depending on its resistance value. So I would say, okay, it's like nutrition, right? Big guy needs more nutrition, small guy needs small nutrition. So bigger resistance will consume more voltage, smaller resistance will consume less voltage. But how do I calculate? So we use this simple formula which we know from mathematics, that if you ratio proportion, remember ratio and proportion. So it's nothing more than just ratio and proportion. So we take the total resistance, and for the particular resistance that we interested in, we find its ratio with respect to the whole and multiply it with the voltage, that source voltage, and that gives me the voltage drop across that particular resistance, right? Who's the big guy in this room? Maybe I'm the biggest, 280 pounds. So maybe somebody of you is, maybe most of you are much, much, much lighter than me, right? I don't want to pick it out, but so I would, if there was a big resistor, it will consume more voltage. So when you're doing calculation ever and you want to find out voltage drop and you see a resistor with bigger value in your calculations comes out to be consuming less voltage than the other, then something, you did something wrong, right? Just a ballpark thing. All right, so we use this, and once you do this, we call this kind of circuit as voltage divider, but because essentially what we have done is we have taken the source voltage, and now using these different valued resistances, we are using different, we are consuming different voltage in one versus the other. So we are dividing the voltage. So why would it be important? Suppose if I have an LED, one LED is 3 volt, another LED works at 10 volt, but my input is 9 volt, I don't know, 10 plus 3, 13 volt. So I would put a resistance which would consume 3 volts, and then I would put my LED in parallel to this one, because then 3 volt is what will be available across this resistor. And I'll put the bigger LED. Anyway, we'll get there, but remember this, that when we put these resistances in series, we are making a circuit, what we call as voltage divider, because different voltage will drop across them differently. So the larger the resistance, the larger is the voltage drop underlined. And we call this principle of voltage division. Same thing, different ways of how you would name it, or how would you look at it. Again, videos, Robert, Manuel, Juan, Fernando. Guys, this is not sustainable if I have to remind you again and again to turn your voltage off. Oh, sorry, turn your camera on. All right, Mansoor, can you please remind them? Let me make you co-host so you can keep on reminding them to turn their video on. All right, are you with me so far? Help me understand. Is it too simple for you guys? Because I know in high school they go through circuits, right? Yes, no, it's too basic, right? Let me move forward. So now, if you put them, so accordingly, if you have, here it was just two of those, but if you have bunch of resistances, say capital N number of, any number of resistances, and you want to find one resistance with R subscript smaller n, then all you do is same thing. You add all of them up and just divide with all of them, ratio proportion, and you get the voltage drop across any one specific voltage that you are interested in, right? Now, parallel combination. Now, parallel is where the current, all right, so parallel is, okay, you have a voltage source and there's the two resistances which have been placed in parallel in front of that source voltage. Voltage is same across both of those. Well, if the voltage is the same, then the current gets divided across those two paths. So now we would say if there was current I that was flowing in, and that has to get divided now into two paths. So we say R1 on the left, R2 on the right. So, okay, then we'll call it I1 and I2, that the current divided into two paths, right? But this is important that the voltage across these two paths will be the same. V, which is written here in middle as well, right? So, but this is an external voltage supply. So that's going to be the same. Now, treatment for this one is, now we calculate the equivalent resistance by taking the inverse of their, what do you call, 1 over R, inverse of, what do we call when you put something in the denominator? What do we call when you put something in the denominator?
Reciprocal.
Reciprocal, yeah. So we add the reciprocals, and so basically this is inverse of that relationship now. So what's basically happening is we would take the resistances, we would add their reciprocals, and we will flip it. We'll take the inverse of that. That would be the equivalent resistance. The reason is now because the higher the resistance would be the least dominant, because the current flow would be less in the higher resistance. So now think about it, higher resistance would mean less current is flowing. Hence its contribution is taken as reciprocal. So again, this is for two, when we have two of those, or n number of those, as many as would be there, is the same principle that would be used to find equivalent resistance. All right. Now, in this case, the voltage is the same, but the current gets divided. So now current would be this in a similar way, ratio proportion. Current is what we would use by taking that uh, proportion of the resistance. But in this case now, for the current through I, resistance 1 would be dependent on the ratio of higher of those. So which means the current 1 will be the division with respect to resistance 2. So again, if there is higher, this example, if there are two resistances, the more current will flow through low resistance, right? More, because high resistance means high resistance, it's not letting it flow through. So hence this is the relationship for a simple two circuit of two resistances. So current 1 would be the, sorry, it should be I, not V. I'll have to correct this. I just used an old PDF file to make new Word document, and then I was working on this. Right, so total current, more current will be used up in the smaller resistance, right? So the other resistance will define where the more current will flow through. All right, let me make a note to change this in what I've already uploaded. All right, make a note this, that on the handout, the equation right below figure 3, we have to change V with current. All right, so, all right, Amira, I got your message. Don't worry, we'll be recording this session. All right, so let's get going. So now reciprocal of current is another entity. We call it conductance. Just instead of using 1 over R everywhere, we can find G, what we call as conductance, which is G equals 1 over R. And we can, instead of doing 1 over R everywhere, we can just use Gn. So the current conductance proportion can be used to find the current through any number of nth resistor. So if there are a bunch of resistors flowing through, we can use the proportional resistance for that resistor to find how much current is flowing through there. All right, so now this is how would a parallel circuit look like. So what you have to visualize when you encounter this is we have to see where is the common point where they originate from. So this would be a common point if you want to take a look. So, or you can then make it or write it like this, just to show that common point with R1 and R2 summit. So this is the same thing what's been shown here. So we should be able to visualize these things. It seems straightforward thing, the way it's shown, but when a bunch of resistors come together, then this kind of visualization helps you a lot to see that these two resistances are in parallel, and there may be other resistances in series. Suppose if there was a resistance here, then it will become, then you will have to divide and rule, where you'll have to solve this first, and then you will write it like two resistance in series, and then you will calculate that, those two. Does it make sense? Why I'm saying that you have to visualize where are the 2 points between two resistances which creates that small parallel circuit for you to solve. So you'll solve that to find equivalent resistance, and then you'll find equivalent resistance for that resistance with any other resistances. All right. All right. Questions? All right, so we're gonna get into the lab now. The lab has been posted. I'm just gonna, with this correction, I'm just gonna post it again just now. I want you guys to go and open your Blackboard and take a look at that. Let me share the Blackboard right now so you can see where the lab is posted.
But we can begin working on it?
Yeah, there's the lab time.
Okay.
So, TA had the parts available last week for Lab-02. Right? So if you didn't get it, let's look at the close values, and we can start doing, at least start building the circuit to have a run right now. All right, so I'm sharing let me switch off the edit mode so I will show you what you will see. So Lab-02 is posted. Again, course modules. You will see module 2 has been just made available, or it was available, it's populated. Objectives, equipment, Lab-02 handout is posted here. Submission link has been made active. And of course, just like last time, you'll submit your video here. All right, with me on this? All right, let me go back. So we go back to the PDF. All right, so on breadboard, you have to create these combinations. So this is a series parallel network. So again, like I was showing just now, you have to go whenever you're doing the analysis, we always go inside out. You start with the most fundamental combination of resistance that you see, and you find that part's equivalent resistance, and you make on your paper a simplified version. And then you go inside out. Then you see, okay, which resistances are more fundamental. So here what you are going to do is you are going to build this parallel network, right? You'll put two resistances in parallel and then one resistance in series. And then we'll apply voltage to it. But right now when you make it, then we have a bunch of things where we have to measure the resistances using a multimeter, right? So, but you have to be careful. You have to isolate one resistance from the other resistances so you don't get any grounding effect there. You get your resistances. Now you'll calculate what should be the total resistance or equivalent resistance. And you'll put the calculation there. And then you'll measure the total equivalent resistance using your multimeter. So then you have to use a simple equation to find what is the difference percentage error, right? From what you expect in reality and what you get. Now this relationship you would use throughout the lab. Basically, in all cases, you will have a value you'll calculate what you expect from the numbers and a value that you would measure. And we would want to see what is the percentage difference from calculation and the measurement. Can somebody tell me where would that difference come from? Why would there be a difference?
Because there is like a theoretical value and then an actual measured value that we measure with the voltimeter.
Right, you just repeated what I said. What is the source of that difference? Why would there be difference? Yeah, we agree, Carlos and I agree. There'll be a difference between what we expect and what we measure. What is the source of that difference? Why is there difference?
Because of probe resistance.
Okay, because of the probe resistance, that's number one. Number two,
Human error?
human error. Okay,
Yeah.
number two is human error. Number three, you can avoid human error, but there are a few things you cannot avoid. Remember that silver and golden stripe on your resistance? What does that mean? So
Tolerance.
tolerance, right? So tolerance. So the values of resistance can be off by 5 to 10%. For one resistance, that can be off 5 to 10%. And then you have a bunch of resistances connected. What do you think is going to happen to those tolerances? They're going to become bigger, right? So each one will be contributing to that, some offset up or down, right? Contact resistance. So when you have things you're connecting and your breadboard, there is a contact you're making. So there is a contact resistance as well that comes in. There are a bunch of sources that of course, when you have your 9-volt battery connector, right, there's that connection also, which is introducing some resistance of itself. So there are a bunch of sources that come into play. Right? So that's why we need to know what is the percentage difference, and not just for for the voltage, for the resistance, for voltage, for current, for everything. And that's what we will do when you go further in this lab. So then you'll put the 9-volt battery in it, in the circuit. You'll connect it in the circuit. And then you'll calculate what you expect. So calculation for current. Now, can somebody tell me the relationship between I1, I2, and I3 here? If you were to write an equation between I1, I2, I3. Help me write this equation. Can somebody tell me how would I write an equation for I1, I2, and I3?
Will it be I1 equals to I2 plus I3?
All right, very good. That's correct. Right. But that's a very simple thing that Carlos said that, right? Yeah, fantastic. So these are things you need to know while you're doing this. At least in this lab, of course, things are going to get more involved. So how will you calculate current? What are the two things that are available to me here? I don't know the current, but what else is given or available?
Voltage,
Voltage and
resistance.
resistance. So Ohm's law, right? Write a big Ohm's law in your room, because we'll always be using that thing to, two things are missing. One thing needs to be found out either by calculation or either by measurement, right? Ohm's law. So if we have the, but then it's important to know which value to use where. Do I have to add some of those two together? Would I have to uh, find an equivalent thing of something before I apply Ohm's law? So you have to be able to justify the application of Ohm's law on certain values, which values to use. So here you'll be using, of course, Ohm's law to find your currents. How would you find IS? If you find everything else, if you find equivalent resistance, and you know I1 already, should give you your IS, the current coming from the source. All right, very good. So again, here you'll have to measure the currents, not calculate. Again, you'll find the percentage difference. Voltages, you'll have to find voltages, calculate and measure difference between them. Am I going too fast? And we are here. So I just want to make sure you know what we are doing today, and then we'll start doing this. Now, the question is asking how V2 and V3 are related. So you'll have to go back and see. Of course, the numbers will tell you a few things, few hints already there. Then you'll go back to look at the picture, and that will tell you how these two things will be related to each other. Right? All right, then you'll find the KVL application. Does it hold? And you'll show these things in your video also. That will be part of how you have achieved, or you have got there. So that was parallel series network. Now we have series parallel network. Two resistance in series, and then those two are in parallel with another one. If I look from here, how do I get the RT from these three? Which one do I solve first? We'll always start with the smaller network. So two series, add them, and then we'll deal with them two in parallel, and that will give me RT. So, and then you'll measure these as well in your circuit. And you'll calculate the RT from the what you see here and what you will implement on your breadboard, both ways. And that will lead us to finding the difference between those two. All right. All right, so now we'll apply the 9 volt to the circuit. Why do I have so much white space? I think it took off something during PDF formation. But anyway, this is good to go for you guys, except that one correction that we already identified. So now we'll apply 9 volt battery to it, and you will calculate again current between these two lines, current through each individual resistance, and that will come to this part. So we'll calculate, we'll measure again, and that will help us find the difference between those two. How are those currents related? Again, the numbers will give you much information, but you'll have to follow the circuit to see how they are related with each other as well. Questions? All right, so we are almost at the end of this part. Again, record it in the video, save your resistances. Don't jumble them up. That's gonna help you for the things going forward as well. All right, so then you have to, there's after the lab thing, there is a circuit and you have to determine V1, R1 and R2, right? So if you know what you have done, then it'll be straightforward to do this question. And there's space to do, show your work, and there's where you have to give your answers. Similarly, another circuit, you have to find out V1, R2 and R3. Again, power source, voltage. This much current being supplied to the circuit and another one given on this side. So it's a little bit tricky, but same principle. All right. So that would conclude lab 2 for today. Questions? All right, so let's get started. I'll be here. TA is here. We'll probably will have our video off, but yeah, you have a question, just shout it, type it, and you wanna stay, that's fine. You wanna go do it some other time, that's fine. But this is the lab time for this class. All right?
Professor. Oh,
Yes, sir. Go ahead.
oh, thank you. I have a quick question about the videos.
Right.
Do you need a certain length or something? Because
No, don't worry. It's I think I did say some number. How much was that? 5 to 10 minutes, I think. Less than 10 minutes, probably. Mansoor, do you remember what was the time we specified for those videos? I did say it somewhere in probably the syllabus or somewhere. It's supposed to be small, not too long.
it's just that for the last lab, I only recorded myself taking measurements of the resistors, and it was only like less than a minute. So that's why I was asking.
So see in the handout, there are few places where we specifically say, okay, show it in your video. So as long as you take care of those, that this addresses part 1, section, and there's together and how this is happening. So that should be okay.
So like as long as we show what it asks us in the video, then it's good?
Yeah.
Okay, thank you.
Right. So yeah, there are a few key points where we identify in the lab handout that show it in the video. So at least have that in there. Right? Yeah.
I was gonna ask
Thank you.
if I live in Brownsville, could I get any parts from the Brownsville campus?
Francisco, we cannot hear you. Can you speak a bit louder?
Oh, I'm gonna unplug my.
Can you hear me?
Yeah, now we can hear you.
Okay, if I live in the Brownsville campus, can I get like some parts from this campus?
Okay, so email me and I can email it onward to the instructor because there is a section in Brownsville also. So yeah, we can get you parts from there as well.
Okay, thank you.
Yeah, no problems.
So can you-
All right, so yeah, take it away. You are free to switch off your video and start working on your thing.